Here is a lecture that I've been giving for a while now that aims to present the FDTD method and how it works. So, this computational method has been defined in 1966, and here is the abstract of the founding article. It's actually very old, but it has only been used really for 30 years because it lacks in the form defined in the paper a few components that make it actually usable. In the original paper, it was very bare bone, and actually one couldn't really do anything of interest with it. What does it mean? So FDTD stands for finite difference time domain. First, the finite difference is the principle we are going to apply to our equations on space, which are going to be discretized through the finite difference approximation. The time domain part means that our simulations are going to try to reproduce how light propagates through our structure. And that has some implications that we will see at the end. How do we get this? So here we have the definition of the derivative. So to get the derivative, you take 2 points on a curve, you get them closer and closer, you divide the difference by the distance, and you get the derivative. In the case of the finite difference approximation, we will have exactly this, except that the value h here is not going to be 0 anymore, but it will have a finite value. So let's try to derive that. To do this, we first start with the Taylor expansion, which defines the value of a function when you shift it by a small value h, and this depends on all the derivatives of this function. So when you expand this, so f of x plus h, you get the f of x plus h times the first derivative plus h squared over 2 times the second derivative, and so on. But you can also do it with a displacement on the left, with a minus sign here, and that is going to switch all the signs for the odd elements of this expansion. Now we have those two equations, and we can manipulate them. So for instance, we can subtract them both, and we see that we will have opposite signs, in this case for even terms of this sum, and we have a residual here that is not of interest. And when you do this, we get this approximation, which is the central difference approximation, that approximates the derivative by 2 points around the points we want to evaluate. This is second order accurate because the residual here is second order. We can do exactly the same thing for the second derivative, except here we are going to add them together, and the terms that have opposite signs now are the odd terms, and we get the second derivative approximation, which looks roughly the same, except you combine more terms. It is possible to combine even more equations together, but you are going to add a lot more points to get your derivatives, but in the same way you can get the third derivative, the fourth derivative, and so on. Now, we are going to define some notations. So our space is discretized with steps delta x, delta y, delta z, and delta t, and actually we are going to refer to each point in our grid through their number, which is an integer. So we are going to, x is going to be I multiplied by delta x, and so on. And so we arrive to a discrete notation that is common in books. So f at x, y, z, and t is going to be defined as f of I, g, k, on n. So those three are for space and n is for time. When we use this, it's very convenient because if we were to write all the equations expanded that way, everything would be very, very wide. So this is a more compact way of writing things. Also, when you apply this to our derivatives, so the first derivative of f at the location I, which corresponds to x on time n, so this doesn't change, is going to be f the I plus 1 minus f the I minus 1, so the point on the right minus the point on the left, and we divide it by 2 delta x, which is the space between both points. In the same way, the second derivative is written like this, so we combine I plus 1, I on I minus 1. Okay. So let's try this on the wave equation to show simply how it works. So we have our wave equation which combines the second derivative along x and the second derivative in time. So we apply our notations and we replace this with our approximations that we had before, and we get a big equation that combines all the different terms for the points on the left, on the right, and the times before and after. And this equation actually gives us the value of f at a new time, so n plus 1, depending on the time, the f at time n, f at time n minus 1, so in the past, and the values of f around this point. So this equation is exactly the FDTD but applied to the wave equation. So this alone should be able to run a simulation of this wave equation. Now we are going to look at the FDTD itself, but we are going to do it simply with the 1D case. So instead of the wave equation, now we want to compute the propagation of electromagnetic fields, and to do so we are going to focus on the Maxwell equations. Those are going to be what we discretize. So there are 4 Maxwell equations, so 2 in divergence and 2 curls equations, and we are going actually to focus on those 2. Now, when we have this, how many equations do we actually need to solve? Since we are in 3D, we have 3 components per field, so we have actually 2 times 3, that's 6 equations in total. Okay. Now we are going to change a bit our approximation of the first derivative. Instead of using a full displacement of delta x, we are going to use a half displacement of delta x over 2, which is convenient because we don't have a 2 here, and this turns into this in the notation. This new approximation is actually how the FDTD was defined originally by Kanye, and it's useful to get the leapfrog grid that is pretty convenient for certain boundary conditions, but I will talk about it later. So let's look at it in the 1D case. So in 1D we can, for instance, get only 2 equations that are going to relate to a few components only. And when we apply our approximations, so let's apply the finite difference at location I, we are going to get half steps for the H field over here, and that means that we have a special shift between both fields. So the E field in this case is going to be evaluated at integer locations, and the H field is going to be evaluated at integer plus or minus 1/2. So the fields are not at the same location any longer. Okay? So we can do it the same way for the other set of equations to have a discretization for H. And so we apply again our scheme at I plus 1/2, and we get back the plus 1 over here, which means that the E field is properly defined at integer locations. When you combine all of this in 3D, you get a grid that looks like this. So all the different components of your electric and magnetic fields are going to be defined at different locations. The implication is that when, for instance, you want to have the value of the field at this point, at the origin of the grid, for instance, you can't do this from the computation directly. You need actually to interpolate the field between one grid cell to the other if you want to have something at this point, for instance. And this is true for all the different components. This grid was defined by Kenny this way because it's actually pretty useful if you want to have perfect conductor boundary conditions, because you can they are defined in a way that the tangential parts of the field are 0 and the orthogonal parts of the H field are 0 also. So if we add a perfect conductor on this face, for instance, all the field components on this face will be 0. So everything is aligned, and it's pretty convenient if you want to have your boundary condition on a face of this cube. So we discretized our field in space. We are going to do exactly the same thing in time. So we are going to evaluate this at 1/2 integer in time, and we are going to get again the shift between the E field and the H field. And I'm going to do exactly the same for the other equation, and we get back what we want. So that means that not only are the E field and H field not placed at the same location, they are not evaluated at the same time. So this has implications if you want to, for instance, combine results of E and H. There can be in the software a small phase shift that needs to be taken into account. So here is the summary of our FDTD equation. So this is going to be the FDTD scheme for in the 1D case, and this is going to work in itself. You will be able to propagate stuff in 1D. So this works if you want to try. To summarize what happened, so let's say we are at time t, and we have the E field at the right circle there, and we want to know the E field at time t plus 1. That means we will require the value of the H field on the left and on the right at t plus 1/2. And in the same way, to advance the calculation for the H field, we are going to need now the computed value of the E field at t plus 1 on both sides, and combine it with the value of the H field at t plus 1/2, and we are going to get the H field at t plus 3/2. Okay, now we have a discrete world because we are going to discretize space, and it has implications. So here is an example of what to expect. So let's say we have a standard computer with 8 GB of RAM, and we want to compute something that is 1 micron in size. It is a cube that is 1 micron by 1 micron by 1 micron. And let's assume that a double precision variable takes 8 bytes in memory. What is the finest discretization that we can use here so that everything fits in the computer memory? So here are a few examples. So you can try to guess, but if you want to, you can pause the video for a minute or two and try to guess what it is. But here is how to work this out. So let's say we wanted to discretize this with 0.5 nanometers of spatial discretization. That means that we are going to divide our 1000 nanometer by 0.5, and we take the cube of this because we have 3 dimensions. But we have also 6 fields components, and each one of them takes 8 bytes, so we actually get at the end 384 gigabytes. So this is quite a bit more than the 8 gigabytes that we had. So this discretization is not going to fit in our computer. In the same way, the 1 nanometer discretization is not going to fit because we need 48 gigabytes. So those two are impossible to use for this computer. The 2 nanometer case is going to fit because we only require 6 gigabytes, and the 5 nanometer one is going to work even better. Of course, this only takes into account the storage of the field itself. It's not all the other methods that we need memory for, like the PML, the materials, and everything. So this is actually a low estimate of what we want actually in a simulation. So in this case, the correct answer would be more or less 5 nanometers. Okay. There is another issue in our discrete world, is that all our structures are going to be discretized. So here is an example. This is a particle that has been discretized, and this is the field that has been computed around it. And what we see here are what we call staircases. Because the grid is orthogonal, it doesn't really match the curvature of this particle. What this implies, you can see it on the figure, is that you can see hotspots around the particle. Actually, those hotspots are not real, so to speak. They are really created by this staircase mesh, which has some very pointy tips everywhere. And in electromagnetics, when you have something that is very pointy, you know that the field around this point is very, very intense. So this is basically what we see here. So one must be aware of this stuff, and it can be very tricky because sometimes you can see in papers that people say that they have a field enhancement that is very, very high, and actually if we were to look, for instance, at this point, this is the maximum, it will be very high, but this is only due to the discretization. So if you wanted to compute the actual proper near field very close to the particle, you need to be very careful because you need to smooth things, etc. There are methods in FDTD that try to mitigate this stuff. You can see that sometimes in softwares, methods that try to smooth things, they all have some advantages, but they all have advantages in specific cases. from my point of view, what I've seen in my tries, this staircase approximation is basically the middle ground. It's not the best, but it kind of works basically all the time. So this is not very good, and if you want something very fine, you will need to increase the mesh resolution, but there is a limit to it. The other methods work in specific case, but sometimes they are not that great and they can come with other issues. Alright, so something that is very important to consider is that we have a numerical method here. And that means that it's not perfect. The method is just an approximation. And since it is an approximation, that means we have errors that are going to accumulate at every step of our algorithm. And these errors can be so great that actually the computation breaks and diverges to infinity. And so there is a criterion, which is the CFL number for Cronch, Friedrich, and Levy. And this criterion states that the time step is defined by 1 over c square root of this sum here. This is very important because that means the time step is constrained. And roughly speaking, that means that the more you refine your mesh, the smaller your time step will be. So to give an example, if I want to divide delta x on delta y delta z by 2, that means that not only space is going to be increased in size by 8, because 2 times 2 times 2 is equal to 8, but I'm going also to divide the time step by 2. So since I need still to simulate exactly the same thing that includes the same actual duration, that means that I'm going to increase the number of iterations by 2. So if I wanted to divide my spatial state by 2, I'm actually going to increase the actual computation time, the CPU time, by 16, because we have 2 times 2 times 2 times 2. Let's look at some values of what this means. So let's say we have a wavelength of 500 nanometers, and we are going to discretize this with delta x and so on at 5 nanometers. That implies that we have a delta t that is around 10 to minus 17 seconds. So this is very, very small. This will be 173 iterations by period of the light oscillation. Since this is very small, this also means that if one wanted to simulate something that is very long compared to this, relatively, for instance, 1 nanosecond, that would imply that one will need about 100 million iterations, which is quite a lot. So this is very high number. Computations, if they go above 10 million iterations, that's already way over what I usually do. So if you wanted to compute very, very long times, actually this constraint would stop, would be a bit too strong for what we want to do. There are new methods, they have been in development for 15 years, almost, over 15 years now, that tries to mitigate this stuff. There are the implicit scheme, the alternating implicit scheme, and so on. They do work, but they have their drawbacks that are quite big. I don't think there is any commercial software that uses those right now. Okay, now let's look at the discretization again. So let's say, for instance, we have a pulse. So because everything is going to be pulses, all our sources are going to be pulses, basically, in free space, and we have a spectral range between 400 nanometers to 1 micron. So what should be the largest space discretization admissible in this case? So let's say from 5 to 50 nanometers. So again, you can pause here a bit to think about it, but here is how it goes. So in our case, actually, the smallest wavelength that we want to study is 400 nanometer. So this is going to be the limit in our computation. So if we add a discretization of 5 nanometers, that means that we will discretize this with 80 points. If we add 10 nanometers, it will be 40 points. And when you increase the size of your step, you see that the number of points decreases. And at 8 points, well, it's not working very well. And that implies that one must be very careful, because it's not only the structure that needs to be discretized properly, but also the wavelengths that one considers. And this also can these wavelengths, sometimes the input wavelengths can be quite small compared to what you actually want to discretize, but we will come back to this after. So when you look at those discretizations, the 5 nanometers case is actually very smooth behind all those curves. We don't see it. The 10 nanometers one is still very nice, but you can see that the 25 nanometers case is starting to be very polygonal in shape, and the 50 nanometer case is very bad, and it's going to be worse, for instance, if the field travels at an angle, because it's going to decrease the number of points that are actually going to be used to describe these wavelengths. Since we have a discrete world, there is also an issue in the dispersion relation of light. So in the real world, we have the dispersion relation that is written like this. So the pulsation is related to the impulse times the speed of light. In the case of the FDTD, we still have something that looks like this, except that this has become a lot more complicated. So it still relates the pulsation of light to the k vector, but in a way that is very complex. Usually you should not have an issue with this in softwares. This is more or less, let's say, general knowledge in FDTD. This is important to have this in mind, because we are not simulating actual space. We are simulating something that is very different due to the time and space discretizations. Another issue that is more of concern to people that implement the methods is that E, H, and K are not orthogonal anymore. It's something that is due to the grid, the FDTD grid. So this is a problem that is not, I would say, not very present in calculations. This is really something for people that write algorithms for the FDTD. Okay, another issue coming from all this stuff is that the velocity of light in the grid is not the speed of light anymore. And actually, the grid itself has basically a refractive index. That means that light travels at a speed that changes, and this depends on the wavelengths. Here are a few examples. So with the discretization that looks like what we had before. So if we had a 5 nanometer discretization in free space in the visible range, you can see that while the speed of light is very close to 1, in this case when we normalize by C, it's not exactly 1, but it also becomes worse as the discretization increases. So it becomes very, very bad for 20 nanometers of discretization, because we are basically missing 0.3% of the speed of light at 400 nanometers. So this is something that usually you should not see if your wavelength is discretized properly. This is an extreme case, because when you look at the discretization related to the wavelength, you have only 20 points in it, and it's already not enough. Okay. Now, what again is the maximal discretization? We have something different in here. So before we look at that for free space, but in this case we are going to assume that we have particles in our grid that have a refractive index of 4. So again, the spectral range is between 400 nanometers and 1 micron, and we are going to look at several discretizations. So what do you think is the largest space discretization that we can use? So before we could say 10 nanometers, for instance, but now what is it? So you can pause again for a bit, but here is how it goes. So again, our smallest wavelength of interest is 400 nanometers, except that in those particles, since the material has a refractive index of 4, the wavelength in the particle is actually 100 nanometers, and you still need to properly describe those 100 nanometers, which means that if we were to use the 5 nanometer discretization, we would only have 20 points to describe this stuff. And if we increase the discretization step, we can see that this decreases dramatically. When you have only 4 points in your wavelength, or 2 points, actually light doesn't propagate in the grid. It's stuck. It doesn't want to advance. And this can lead to, well, some issue. For instance, I have an example of a friend that tried to compute something that contained plasmons, surface plasmons. And in this case, the wavelength was decreasing a lot when it had the shape of plasmons. So the excitation was around 10 microns, and actually the wavelength of the plasmons was around 500 nanometers. And the calculation seemed like it worked, but actually things were not propagating properly inside the grid. It's not obvious before you look at these kind of problems. So you need to take into account not only that your materials have a refractive index, and this is going to affect the discretization you need, but you also need to have an idea of what to expect in your calculation, because this is going to be very important. Okay, so this first part was about how the FDTD itself is defined and what is the implications of working this way. But basically, we are still in 1966 here, and it was not enough to get the FDTD working, and we need actually additional stuff to get it working. So this is what we are going to look at now. Okay, so let's first talk about the boundary conditions. So we have a boundary around the computational window, and we need to treat this boundary properly. So there are three main types of boundary conditions. We have the PECs, which are perfect reflectors. So that means the boundary of your window is going to behave like a mirror. We have the periodic boundary conditions. In this case, so we say that one side of the grid is connected to the other side of the grid, and this can come with a phase shift or not. And that implies that when the field goes from one side into one side of the grid at the very edge, it comes back on the other side. And finally, we have the PMLs, so they are the perfectly matched layers, which are absorbing boundary conditions. They are very important because they are used to simulate the fact that we want light not to come back in sometimes. So these are going to be useful to emulate free space around our particle, around our structure. And why do we need this? So let's say that our grid goes from 0 to n minus 1/2. So this is in grid notation. And when you look at the 1D equations, for instance, you can see that to evaluate the H field at, the time derivative of the H field at n plus 1/2, we need the value of the E field at point n. And actually, this point is outside the grid. So as far as the equation is concerned, that means that this value is basically 0. So we have the time derivative is going to combine a 0 on an actual value of the field. So what does this mean? What actually happens is that this 0 basically behaves like a perfect conductor. And that means that the edge of your FDTD grid is going to behave like a mirror. And everything is going to be reflected back inside the grid, and it's not very convenient because you are going to have multiple reflections inside the window, and you can't really analyze anything due to this. And here is an example. So this is a simulation at two different times. So in my calculation, I have an oscillator here that is going to emit a field around it. And since there is no specific boundary condition at the edge of my grid, actually the field is reflected. And this is what we can see on the right. So this is at a later time. The field has propagated, so this wavefront comes from the top right over here, but this wavefront actually is what went to the bottom, and it was reflected and is going to propagate upward again, like the other. And if we were to let this run for a long time, this will bounce forever because there is nothing to absorb field in there. So one can do anything with this. And the issue is that the FDTD method was published first in 1966, but the PMLs were actually defined in 1994. And so it took about 30 years before the FDTD could actually be properly used. There have been tries before 1994 by people to define absorbing boundary conditions for the boundaries of the window. So we have the mirror boundary condition. We had a lot of different things that kind of worked. They were working for a very specific case, for when, for instance, the field was at normal incidence on the boundary, or they worked well, they worked for very specific angles, but they were far from perfect, and we really had to wait for the invention of this stuff 30 years after the FDTD was defined. And that means it has only been 30 years since we could use the FDTD. And this concept of PML has actually been applied to other fields of computational physics. I've seen this in methods that were not concerned with electromagnetic fields. And since then, there have been some refinements. So there are the stretch coordinates formulation, the uni-actual PMLs, the shift PMLs in the complex planes. You are going to find this stuff in various softwares, and each one of them has its own properties, its own parameters that needs to be defined. In my case, I use the complex shift PML, and it works kind of well. Okay, so how do they work? So basically, the PMLs, there are a specific material. So let's say we had two media, 1 and 2, and we wanted to make sure that light doesn't coming from medium 1 into medium 2 doesn't come back. And it is possible to find a very strange material for medium 2 so that there is no reflection of light on the boundary between both. But this material is complex, anisotropic, and it combines both E and H, and those are what we call the perfectly matched layers. Perfectly matched because they are reflectionless. So technically speaking, this is how it works. Of course, since we have a grid that is discretized, it's not perfect, and the way to mitigate the actual small reflections that we have, they are small, there is still some reflection when we apply this, but there is still some, is to have actually many layers, one after the other, and we are going to increase the values of the different parameters of this layer. And one way to do it is that we, for instance, increase what is roughly the refractive index of the layer. So as light goes into the PML, it slows down. So this value can be very high, from 15, 25. And we are also going to increase the absorption of these layers so that not only light slows down, it also gets absorbed, so that at the end of the PML, there is basically no light able to come back inside the window. And here is an example where it works. So this is basically a snapshot of the field in 1D simulations. And we have the emitter at this location here, and we have an interface here with a high refractive index material on the left. And we have PMLs on both sides of the window. And one can see that before reaching the edge of the window, we have the field that decreases very strongly because it's absorbed by the PML, so on both sides. So this works, and it's basically mandatory to be able to compute anything useful. Now, we have boundary conditions. We also need a way to have field in the window because, you can't simulate anything if you don't have a light source inside. And we so need to define a source for our field. The basic source, that is the most, let's say, naive, is the hard source. So to do this, we just say that the field at a location is a specific value that is going to evolve through time. So for instance, a sine wave. The issue is that just like for when we wanted to investigate why we need PMLs, this value is going to be defined always by this equation. When you want to update the FDTD equation around it, if you have field coming back, it's not going to propagate properly on those kind of sources, tend to reflect the field that is going to hit them. And so what is better is to have transparent sources, to have the field go through the sources, and to do so we can modify the previous equation by making it cumulative. And in this case, the FDTD equations are going to be able to propagate field through the source, so this works. What you're going to find basically everywhere is the total field scatter field formulation. That is very useful. That is also a transparent source, and we are going to look at this. So the TFSF formulation basically splits the grid into two grids. So one grid is going to contain the total field, and the other grid is going to contain the scattered field. So here is basically how it works. So we take the FDTD equations, and in them we add new terms that are going to correspond to the source. When you look at how it works in a calculation, so here I have, so this is the edge of my computational window. Inside I have a particle with a very high refractive index, and I have around it, you can see a boundary, that is the boundary between the total field and the scattered field. So in this calculation, actually what the TFSF formulation does, it actually injects the source on this boundary, and this the incident field is now included inside the boundary, but field that has been reflected by the particle is going to be reflected also inside the boundary, but it is able to escape it and reach the scattered field domain. This is a very useful formulation because, for instance, here we wanted to compute the cross-sections of these particles, so we have the absorption cross-section. To compute the absorption cross-section, we will need actually to put a sensor around the particle, but this sensor needs to be able to detect the incident field. So the sensor is going to basically not absorb, but is going to be recording what field goes inside the sensor. So this is incident field, but it also will need to record the field going outside. So all this information is contained in the total field domain. At the same time, we might want to compute only the scattering cross-section, but for this purpose, we only need the scattered field. So we will put a sensor outside the TFSF boundary, and this sensor will record only the field that goes through it, but that it will only be the field that has been scattered. And this TFSF formulation is basically used roughly everywhere when you have plane waves. So this is very, very important. And I think that every commercial software now uses this method because it's very, very efficient and it works very well. Okay, now let's talk a bit about the time domain, because as I said, we are working in the time domain, so we simulate the propagation of light inside our window. So what does this mean? Actually, when we do our calculations, we are able to compute many wavelengths at once, because our simulation is time dependent. there are simulation methods that are not written in the time domain, but in the frequency domain. In those cases, the calculation is done for every wavelength separately. It can be tricky because, let's say you have a very sharp peak in your spectrum, you might really miss it if you were to use too few points in your frequency domain simulation. But it's pretty easy to put basically as many points as you want in your spectrum in a time domain simulation, because you simulate everything at once. Of course, the more points of analysis you have, the more memory your computer will require, because you need to track everything, and of course this is not infinite. The issue is that since we work in the time domain, we need to know the time description of many things, notably the materials. And also, when you want to have the spectra at the end of your calculation, you will basically need to have a Fourier transform performed everywhere on every single data that you want to extract from your calculation. So let's talk about materials a bit first. So the FDTD equations that you have seen before, they add the epsilon coefficient or the new coefficients in there. Those coefficients are going to be constant in the calculations. And so they are not enough to describe media that are complex. For instance, metals that are dispersive, some glasses that are dispersive, and so on. They need something more. And that means that we're going to add new equations to the FDTD, and those equations, their task will be to describe those materials, but we need to be able to have time equations. So those equations are going to iterate through times, just like the FDTD method itself. So one way to do it, this is called the recursive convolution method. So this works for linear optics, and in the time definition of the response of a material in linear optics is written this way. But that means that we need to know the susceptibility of the material as a function of time. And the issue is that not all dielectric models are going to work for this. That means we are restricted to a few of them, and for instance, it can be very complicated to describe some semiconductors with this stuff, because you don't really find a dielectric model that is going to fit the refractive index properly. Also, that means that you can't just put in your calculations, let's say, for instance, the refractive index you got in experiments. You need to fit the refractive index with a dielectric model that the method is going to be able to comprehend. So no tables of refractive indexes, nothing like that. You need to fit everything. So it can be a time-consuming step when you don't know what to use. And this is something that usually is done by before you. It's the models are included in the software, or for instance, in the case of numericals, they fit it on the fly, but it comes with a problem in itself. Okay, so let's say this works, and we discretize this in time, and that means that as far as the FDTD is concerned, we are going to have a new equation that is going to describe the material alone, and we are going to have new terms in the FDTD update equations that are going to be related to the method. So this is one way to do it. So this is one way, one algorithm that works in this case. This is not the only one. For instance, there is another method that is called the auxiliary equation method. So let's say we have a dielectric model for our material that looks like this. In this case, we are going to use the current density to relate the current density to the E field. So let's say we have this in the frequency domain. If it's a nice fraction-like model like this, we can basically multiply both sides by 1 plus, well, all this stuff. But we can perform on this an inverse Fourier transform directly, because those terms turn into time derivatives. This is in the definition of the Fourier transform. This is very convenient. And we can discretize this stuff. And so we get the new equation for the current density. So this is a new update equation that is going to be related to the E field in this case, and we can inject the current density in one of the curl equations. So that way we can describe the material. Okay, now there are some problems. So as I said, we can only use some very specific stuff in our models, so no arbitrary material that is very exotic or that you can't fit with a dielectric model that works. Another issue is that since we have materials now with their own equations, they are going to require some memory in themselves. So the more complex materials you have, the more memory they will take for their own calculation. And that also means that you will increase the number of equations that you need to update in your algorithm. And so that will increase the computation time of the total computation time of your simulation. And also, since we have discretized equations, again, we have a new stability criterion. But this criterion is very complex. It depends on the spectrum, it depends on the parameters of your dielectric model, it depends on the mesh, it depends on if you have evanescent waves inside on what they hit, it depends on the algorithm that you're going to use, and this is very, very complicated. There is no... Well, there is some attempts to describe this properly in the FDTD literature, but I don't know if softwares expose them properly, and it can be very complex. The issue is that sometimes you will see that your material is going to behave very strangely, and for instance, let's say you simulate something, it seems to be working well at first, but as the simulation goes on, you start seeing actually the field increasing inside the window. This is due to a material that is unstable for all this stuff, and it's going to start emitting light in itself, so it's a very, very problematic issue, and you can't really detect it before, and so you need to be very critical of what your calculation does. You can even... I've seen this in my experiments. Let's say you have a material that seems to behave properly, there is no field emission, but actually what happened in my case is that the material became transparent, even though it should not be transparent, because this instability was perfectly counterbalancing the absorption of the material. So I had basically no way to detect that the material was not behaving properly, except by looking at the result. There was no way to say, for instance, that the field was increasing exponentially, and it was the computation was corrupt anymore, but I had to look at the output data and be fairly critical of it, and you need to have this in mind, because I've seen this even in commercial softwares. I've seen friends have issues with numerical, for instance. I've seen this in my own calculation of my own software, and sometimes it just happens and you have no real way to do anything about it except changing things a bit, and it can be tricky. But yeah, of course, those cases are fairly rare, so don't believe that it doesn't work, that it never works, because we will not be able to simulate anything if that were the case. But these things do happen, and you need to have it in the back of your mind, because when it happens, you need to be able to detect it. Okay, another issue is when we want to use periodic boundary conditions on oblique incidents. And this is fully related to the fact that we are working in the time domains, and this is going to happen in every simulation method that is working in the time domain. So let's look at how it works. So this basically is a window, and in this window we have a pulse that is propagating. So you see here the intensity of the pulse in space. The issue is that when this pulse is at an oblique angle of incidence, what is happening on one side of the window doesn't match what is happening on the other side of the window. And your field has a very strong discontinuity, which means that on the edges it's going to diffract very, very strongly. And we can look at this as a time problem, in that the value of the field on one side is going to match the value of the field on the other side, but at another time. And this is a very, very big problem, because we need a way to match both sides of it. And there are some algorithms. First, I'm going to talk a bit about one case I've seen. One case that I tried to implement. It was an algorithm that supposedly was working very well. It was recursive, and well, it involved quite a lot of work on my side. But no matter how much I tried to get it working, it never worked, because there were some, let's say, things that were not said in the paper, and there are only a few methods that work. One of them is using the Arminian-Ramadsamy method that relies on block boundary conditions. So those block boundary conditions actually are based on a phase shift of your field at the boundary. The issue is that this phase shift is unique for all the wavelengths. So this phase shift is defined by a k vector and the length of your window. But since this is fixed for all wavelengths, as we want to have a broad spectrum, that means that we have a relationship between the wavelengths and the angle of incidence. And so that means that when you do a simulation, when you run a calculation, actually this pulse is going to be constrained by one of those lines on the right here, and your wavelength, the angle of incidence, is going to increase together with the wavelength. In the extreme case, when you look at those curves, for instance, you can see that they reach 90 degrees. That means that all the wavelengths on the right are actually going to inject evanescent fields inside your window. So this is something that one needs to take into account. And also, if you wanted, for instance, to have an analysis at a fixed angle for all the different wavelengths, you would need to do all those calculations, all of them, and interpolate the results on a line that goes through the angles that you want. So if I wanted to have something at 45 degrees here, I would basically have to run 20 simulations and do the interpolation. And so this is very, very time consuming. And if possible, try to avoid oblique incidence in FDTD. If you can't, you need to have this in mind. Now, for instance, in numerical, this is defined in the source input window. When you define your source at an angle, they do show a bit of those curves to show the variation of the angle of incidence. So this is very very annoying, because it makes the FDTD method on basically all the time domain methods that try to use this very hard to use at oblique incidence. It is possible to use it, but it's not very convenient. And to illustrate this, for instance, those are the equations that are going to define the field at the boundary where we want to inject our field. And you can see that the shape is very, very complicated, and this is why we inject evanescent waves in there. At the bottom, you see a simulation where this oblique field has been injected. Since we have something periodic, that means we need to be able to inject it on a plane, but this field is going to expand as it propagates. You can see this simulation at 3 different times, and you can see that the field, the pulse has expanded in a way that is very that seems unnatural, but actually this is the only way for this stuff to be an actual solution of the Maxwell equations and to be able to be propagated inside the window. Okay. Finally, let's discuss a bit about the simulation analysis issue. So we work in the time domain, and that comes with some issues. So let's look at a concrete problem, for instance. Let's say that we have in our window a structure that is made of nanorods that are resonating at 1.5 micron, and we have an analysis spectrum that goes from 1 to 2 microns. And let's say that the pulse that we send in there is 5 iterations long in time. So how many iterations should the calculation run for? So 5,000, 10,000, 20, 50. So you can pause a bit, think about it, but let's look at actual results. So this is an actual case with a nanorod that is resonating at this wavelength, and those are the reflection. So this is a grating of nanorods. Those are the reflection, transmission, and absorption that I got from the simulation after ending it at 5,000 iterations. So we have something, the calculation returned something, but this looks very, very strange. You can see some very big oscillations in the spectra. So, well, this is not an issue in itself, but this doesn't look very natural. You can see here that the transmission goes above 1, and you see that the absorption goes below 0. So, of course, that means that the result is not proper, because absorption below 0, in all your calculation, absorption below 0 means that something went wrong, because that means that you have defined that you have somehow created energy inside your window. So this is a good way to see if your calculation went completely wrong or if there is something missing. If I increase the computation time to 10,000 iterations, we start seeing something. So we start seeing this resonance of our stuff, but we still see some oscillations. Okay, so we can still say here that this is not proper because we still have negative absorption over here on those oscillations. Doesn't look very natural again. If I increase this to 20,000 iterations, you can see that now we have something that looks very smooth and that is very that is basically what we expect, what we were looking for. But if I increase this to 50,000 iterations, we see no change. So that implies that the 20,000 iterations were enough to get this working. On 50,000 were actually too much, and we basically wasted time computing it for nothing. So this is actually something to keep in mind also, that you can put many iterations, but some of them are going to be wasted computing basically 0, and that's it. Okay, so let's talk about the Fourier transform and what it implies. So we are going to do some Fourier transforms basically everywhere in our analysis. And so the Fourier transform is defined this way, but what we actually do is that since we need to end the calculation somewhere, this integral, and not only does it end somewhere, it starts somewhere. So this integral goes now from 0 to a maximum time, while it should go from minus infinity to plus infinity. So what we get actually is the Fourier transform of our signal multiplied by a box, okay? And that means that actually the spectrum that we wanted to have is going to be multiplied, well, convoluted by the spectrum of the box, and so this is not what we want. Basically, the spectrum of the box is what we see here, for instance. Because my calculation was cut short, we get this box, so those oscillations are basically the signature of this box in the formula over here. Okay, so this is a very important point in that you need to leave your stuff running for long enough so that you don't cut your signal short. Basically, you need to make sure that there is, at the end of the calculation, there is no field remaining inside the window. In softwares, there are ways to, usually there are ways to compute this basically automatically. You have a termination criterion that you can define that is going to be, let's say, for instance, looking at the total energy in the window, and you say that when there is very little energy remaining, you stop the calculation, and you hope that this was low enough that you don't have this issue. A very big problem is that you can't really predict sometimes how long it's going to take. So, for instance, in this case, we had a resonator, and this resonator was basically resonating for quite a long time, and you can have the case where the resonator is so good that it resonates for a very long time, and you basically have to wait until it stops resonating. You can also have the issue when you have specific modes appearing in your window, for instance, guided modes or planar modes that are going to propagate inside the window for a long time, and you need to wait for them to exit. And this can be an issue when you have gratings. So this is something to keep in mind also. Well, this works, and you can get results, of course. Okay, now let's conclude on this. So, the FDTD method has many issues. So this is very memory and CPU intensive, and the mesh that you have in your grid is not really suitable for stuff that is curved or any very strange geometry. It really likes things that are straight. That means that when you have something that is curved, you need to adapt the mesh so that it's very fine around this curve. Since we work in the time domain, we have Fourier transforms everywhere, so that means extra calculations, of course, at the end of the simulation. We have to wait for the calculation to complete, so as I said, that can take a long time if you have something resonating for very long. Oblique incidence is a big problem. Of course, it would not be used if there were only issues, and the FDTD has some advantages that are very, very nice. The first one, this is for programmers. It is quite easy to implement because it's much simpler than many methods that can be found in books and in papers. It can also be parallelized very easily, so because we have a grid, points of a grid only need their neighbors, you can parallelize the grid itself, and this is very nice. And since we work in the time domain, we have a multispectral response in our calculations, and this is very convenient because you basically compute everything at once. Also, since we work in the time domain, that means we can work with non-linear materials. So that implies nanolasers, some semiconductors that have levels, atomic levels, and so on. So that can be very useful, and you can find this in papers. Sometimes where they can compute fluorescence, they can compute nanolasers in cavities, and this can be nice. It can be found in some softwares at the moment, but it's also very complicated to get working properly. And here are a few references if you want to dig into the subject a lot more. So those are basically stuff, the basic stuff that you need to start working on an FDTD code. And if you really want to be able to implement something, well, you need to find this book from Taflov on Agnes, and this basically contains everything, and this is what I've based most of my work. And so, but this is a very, very big book with a lot of things in there, but this is basically the Bible of the FDTD.